Hello and welcome to part 2 of the lighting video for how to make a game like Minecraft in Unity, part 16 of the series overall. And in this video we are going to make the basic lighting work. In the last video we got our shader up and running so that we can, the foundation blocks essentially, and in this video we're going to get just the basic sort of light propagation going. Smooth lighting will be in another video because we're going to need to do some more work on the shader. You may have noticed it doesn't look great at a distance, so the shader is not done, but let's just get some proper lighting going to start with and then we'll work on that later. Before we get to that, there is one thing I want to address. I did have somebody comment on one of the previous videos. I can't remember your name, I apologize for that, but you mentioned that you had some kind of issue with null reference exceptions or something to do with the threading. Now, I hadn't experienced this problem until I was working on this video, so I was going to fix it until I sort of got digging around in the new Unity job system, and well, long story short, we're not going to fix the issue that is there because we're going to completely change that whole system. We're going to move away from the threading system that I wrote and into the Unity job system because 1, it's easier to use, 2, it's neater, and 3, it's faster. All of those things are great. So for now, if you have been experiencing any issues with the threading thing, we're just going to put a little flag that we can use to turn threading off easily. So if we go into our world script and then somewhere at the top here, this will do. We'll just put a nice and simple, you know, let's start putting some headers in here. So this one we will call header game generation values. Oh no, sorry, world generation values. And then all of this, well, these two are world generation values. And then under here, we're going to have another header, which we're going to call performance for now, for lack of a better term. We are going to have an episode on handling the settings and stuff properly. So for now, it's not massively important. It's just making things a little bit neater. So in here, all we need for now is a public bool enable threading. And then, now the only places we're really using threading right now is here and here. So what we're going to do is we're going to enclose both of those in an if statement. So we say if world.enable threading, then do this. And we just say else. We just call it without populate voxel map, and then do the exact same thing down here. So that will obviously slow the game down quite a lot, but I've only had one person say they've been experiencing this problem, so maybe it's not been a problem for the rest of you, I'm not sure. If it has been a problem and it's getting on your nerves, just disable it for now. It will slow the game down, but like I say, we're going to be bringing threading back in an entirely different way, and I'm going to do it in the next video so that you're not going to have to wait long for that one. So the next Minecraft video will be on the Unity job system, so you've got that to look forward to. So now if we just go into our world script, or into our world object, sorry, and up here somewhere we have enable threading, we just uncheck that, and eventually we have our world. And obviously if I try and walk off in this direction, we're going to get a bit laggy because the threading is no longer enabled. But like I say, this is temporary, and you can enable the threading if you've not been getting any issues with it. So now that that's done, let's get onto our lighting system. So the first thing we need to do is we need to go into our world script, and we just need to change the name of one of these variables in block type, and that is the isTransparent variable. Now the reason we're going to change the name of this is because it's not technically accurate, or it's not going to be accurate for the way we're going to use it. Right now it's saying, is this block transparent? If it's transparent, we want to render the faces around it because we can see through it. So while that's technically kind of true, there are blocks that we're going to add that we need to render the faces around it, but the block itself isn't transparent. So an example of that would be a plant or a torch or stairs, for example, or a half block, something like that. Those blocks we're still going to need to render the faces around them, but the block itself is not transparent. So even though it's only really a semantic difference, we're going to change this to say render neighbor faces, and then we just need to go through and fix any references to that, obviously. So just go through your code, find any errors because there's a call to isTransparent, and change them to isRender faces, render neighbor faces. And that's that. And then if we go back to our block type, we are going to add another value, but this one's going to be a float. And it's going to be called transparency. And we'll get to how we're going to use that shortly. So the next thing we want to do is we want to go into voxel data, and we're just going to add a couple of values in here. There's no headers here because this is a public static script, so there's no inspector values we can change. So let's just put a little comment here, just so we know what's going on in the code. So we need a public static float, and we're going to call it min light level, and then we're going to make it equal 0.25 for now. You can play around with these values all you want. I'm just giving the... actually, no, we'll go 1.5. I'm just giving values that I've come to while I was working out the code, but you feel free to play around with these values and set them to whatever you want. We'll go with 0.8 for that one. And then the final value, public static float, light fall off. And for this one, we're going to put 0.08. Right, now to explain what's going on here. Right now, we have in our world script, in our world object, our world script and our world object, we have this global light level, and it's basically just between 0, which is, oh sorry, well it's backwards, we're going to fix that as well. But it's between 1, which is completely black, and between 0, which is whatever colour the texture is. So absolutely no modification, whatever colour is in the texture, that's the colour that 0 is. And then if we slide it all the way to the black, it's completely black. No texture at all, it's just a solid black colour. Now, that's great, but it doesn't leave you anywhere to go. It means that your range is both extremes, and if you want to have Minecraft's sort of moodiness setting, where you can make the whole game slightly darker or slightly brighter, then you can't have that, because obviously your current range is all the way from one extreme to the other. So what we're doing here is we're giving it a range that it can be, and it gives you a little bit of room either side, so you can move the range down, so you can make it 0.05 and 0.7 or something like that, and that makes the whole game a little bit darker. Or you can move it up to 0.25 and 1, and that makes the whole game lighter. So that's what we're doing there. And then we want to go back into our world script, and we're going to go all the way to the top. Well, not all the way to the top. And in our start, we need to reuse our new shader.set global float. We'll just copy that and change our mins to maxes. And then we're going to just copy that name, because remember, whenever you set a value in a shader, you don't get an error for misrepresenting a label, it just doesn't work. So we need to make sure that this name is correct in the shader. And we go down to where our values are set, or declared even, and we declare them. And don't forget, if you're copying and pasting like I am, to make sure that you get min and max. And now that we've done that, we need to alter this code down here to make use of these. So I'm going to break this up. This could all be on one line. I don't know if it makes a difference performance-wise, but I'm going to break this up into different lines just so you can see what's going on a bit clearer. So we separate these out. It's just this line here in the middle that we're going to be affecting. So I'm just going to separate these, give us a bit of space either side so we can see what's going on. So the first thing we're going to do is we're going to change float, well, let's comment this out for now. We're not going to use local light level as a variable because, again, that's no longer going to be accurate for the way we're going to be using this data. So we're going to call it shade. And shade is going to equal max global light level minus min global light level. So that gives us our range amount. So if you imagine if the range was minimum 0.25 to maximum 0.75, our range would be 0.5. That's the amount of light range that we can cover. And then we times that amount by global light level. So that's whatever this value is here. So that gives us our percentage, because if you remember, it's from 0 to 1. So times in our range by this value gives us our percentage of light. So if this was 0, then our percentage of light would be 0. And if it was 1, our percentage of light would be 100. So we times it by global light level, and then to get the actual light level, we add back our min light level. So just to visualize that, if you imagine that our min light level was 0.25, like I said, and our max light level was 0.75, we'd be saying 0.75 minus 0.25 equals 0.5. Then with that 0.5, we'll be timesing it by, let's say our light percentage was 40%. So 0.4, and that would give us a 0.2, I think. Yes, 0.2. So with our 0.2, we then add 0.2 plus our minimum light percentage, which was 0.25, and that would equal 0.45, and that would be our absolute light value. So we're only using 40% of our available light range. Remember, we could go from 0 to 1, but then we'd have no room to move around. And then we're adding the result, which is 0.2 in this case, onto our minimum light range, and that gives us our final light value. And if our minimum light range was 0.1 rather than 0.25, then this would equal 0.3. It would be darker, but we'd still be using the same percentage of our available range. Hopefully, I didn't butcher all that too much. So let's just finish writing the rest of the code there. So then we want to do shade times equals i.color.a. So if you remember, i.color.a is the value that we passed in using the vertex of the actual chunk itself. Each vertex we assign a value, and this is that value. So this modifies this sets the light value, and then this modifies it. And then finally, we want to do shade equals clamp. So first off, it's shade is the value that we're clamping. Min light level is the minimum, and max light level, max global light level, and max global light level there. Min global light level even. That clamps it between our minimum and our maximum. However, we want to change it so that this here is 0 at the bottom and 1 at the top. Right now we have to have it backwards because of the way the lerp works, because this lerp is lerping from our color to absolute black. So the way we're going to do that is we're going to say 1 minus shade. So if we do a little comment math again, if you imagine that the value itself is 0.95, which is almost completely black. However, if we say 1 minus 0.95, the answer is 0.05. So we can, by doing this, we can reverse what we pass in. So instead of passing in nearly 1 to get almost black, we can pass in 0.05, because if you look at this the other way, 1 minus 0.05 equals 0.95. So we're passing the right value to here, even though we get to use 0 for dark and 1 for light. And again, I understand I'm not the best at explaining this, so if you struggle with any of this, just feel free to leave a comment and I'll try and explain the specific part that you're struggling with. And when I say struggling with, I mean struggling to understand me, not struggling to comprehend the code. So then down here, we want to be passing in shade rather than local light level. So now we want to go back into our chunk, and we want to go all the way to the bottom, and we're going to create a new class. And we're going to call it voxel state. And with this voxel state, we're going to be replacing our voxel map. It's no longer going to be a byte, it's going to be a voxel state. But first, let's get the data that we need in here. So obviously we need a byte for the ID, and then we need a public float global light percent. So what this is this is the percentage of the global light, whatever the global light is. The global light is set by this value here. Whatever that value is, this amount here between 0 and 1 is the percentage of that light that this block is getting. So if you imagine a block directly under sunlight, we'll be getting 100% of whatever the global light value is. And the reason we're passing in a global light value rather than just a number is because that's how you get your day and night. So the global light value at any given time isn't necessarily going to be the same. So this is a percentage of whatever that light value is. And we just need to put some constructors in here. So say public voxel state. And we'll just give it a plain constructor for nothing at all, in case we don't want to initialize it with any values. So that's essentially a dark air block, 0 ID and 0 light percent. But the one that we're probably going to be using most of the time we'll just copy that, only this is going to equal ID. Now if we go to the top here, we want to change our byte to a voxel state. And then we need to go and fix all the references to our voxel map because they are now all in error. But fortunately, for now, all we need to do is add .id to the end of each voxel map reference. And then we're just setting the byte. That's all the references in there. I don't think we reference voxel map anywhere else. Nope. Okay, so that's all of those. So back in chunk, we need to change our populate voxel map here. Now this line will no longer work because you can't set the ID of a voxel state before the voxel state has been initialized. So what we need to say instead is we can just delete that ID that we've just added, and we'll say equals new voxel state, and then we initialize it with the value that we're getting from our world.getVoxel. So that fixes that potential error. And then if we go down to update chunk mesh, I think it's called, or update voxel mesh, update mesh data. And the first thing we're going to do actually is somewhere up here. Right, we're going to steal this code here, and we're just going to change this part here and just set this to XYZ. And the reason we're going to do that is because we're going to need to use XYZ again, and I don't want to have to recast the float every time we want to use XYZ. So we just do it once at the top here, and then we have it ready. If I were to go back and do this again, I would be using vector3 ints all over the place. I didn't even know vector3 ints were a thing when I first started this series. So the next thing we need to do is we need to modify a lot of functions that are currently bools to return whether something is transparent to return a voxel state, like check voxel here. Make that voxel state, and then this one here is just going to return the voxel map value. To fix this one, we actually need to go into our world script, but we'll do that in a second. First off, there is another function somewhere in here. Get voxel from global, I think. Let's just do a quick search. There we go. Get voxel from global vector3. This also is going to return a voxel state. So all we need to do to have that return a voxel state is delete the ID again that we added very recently. Now, if we go into our world script, I'm trying to remember what we've got to change in here. We want check for voxel, I think. Check for voxel, yeah. So in check for voxel, all we need to do there is stick .id on the end of this here. So that fixes that function. And then also this one, we're going to change completely. So it's going to become a voxel state, and we're going to change the name as well because it's no longer for checking if a voxel is transparent. So voxel state, and we're going to call it get voxel state. So for returning false here, if it's outside of the world, we can't do that because it doesn't have a bool state. So we're just going to return null. And then here we delete the block types part and just return the voxel state directly. And then from here, we just need to do new voxel state, and we're passing in the get voxel reference. So if you remember, this is for a case where we can't get a voxel from a chunk, but it is a chunk that's in the world, so we just generate the voxel wholesale from our get voxel function. So in order to return it there, we just make a new get voxel state and put our get voxel ID into it. So now if we go back into chunk, this is now get voxel state. And what else do we have here? Right, so we're into the actual update mesh function now. This is where the magic happens. So the first we can do is comment this out, because this is part of this code here that we aren't using currently, but we will be using in the future. We want to go down to here, and inside there we're going to create a voxel state neighbor equals check voxel pos plus I could have just copied this. So that gives us a voxel state of the current neighbor that we're looping through all the faces of. And then in this statement, what we're going to say instead of this check is, well, first off, what we're going to say is neighbor does not equal null, and then world.blocktypes neighbor.id dot render faces. Render neighbor faces even. So the first thing, we're making sure that we actually have a voxel adjacent to it in the face that we're against the face that we're currently checking. And then if we have that voxel, we check, is that voxel one that we're supposed to be rendering faces against? Because if it's not, we don't want to render faces. And then the next thing we're going to do is we're going to delete all of this, and we're just going to say float light level equals neighbor dot global light %, because at the minute the way this code was set up, we're assigning a light value to a block, and then that whole block has that light value. All of the faces have that light value, but that's not really the way it works. Any given face is going to be lit up by the block adjacent to it. So a right hand face isn't going to be lit up by its own block, it's going to be lit up by the block to the right of it. So that's it for there. Now we need a new function to actually calculate what those light values are. And I'm sorry, this is very code heavy to start with before we actually see anything happen. So if we go up to our update chunk, we're going to stick it under there somewhere. We will call it void, we'll just call it calculate light, I think. We can always change the name later. Doesn't need to take in any values. So we're just going to copy this here because we need to loop through everything. And you may have noticed that I only copied X and Z, and that is because we need to do something slightly different with our Y. And that different is we need to work from top to bottom rather than bottom to top as we've been doing. So Y is going to equal voxel data dot chunk height -1, because otherwise we'd be out of the bounds of the array. Y is greater than or equal to 0, and then Y minus minus. So that is looping downwards from the top of the chunk rather than upwards from the bottom, which is what happens in all of these other loops that we've been doing. Now what we're going to do here is, if you imagine, we're going to start at the top of the chunk with a light ray, which we'll just call light ray. And it's going to equal 1f. This is essentially a percentage of the light above that we were talking about before. So if it's high noon or whatever and the sun is in full force, then this value would be 1. It would be 100% of whatever the global illumination level is currently. So we start off with 1f. There are no obstructions at the very top, and then we're going to increment down each column of blocks. So for every Z and X position, we're going to start at the top and work down, and we're going to modify this light ray value all the way until it reaches bedrock and set the values as we go. So for each block, we're going to create a new voxel state, which we're just going to call this voxel, and this voxel is going to equal voxel map x, y, z. Sorry, that shouldn't be in brackets. And the first thing we're going to say is if this voxel.id is greater than 0, then light ray equals world.block types this voxel.id.transparency. And we need to set those values in the inspector before, let's just quickly do that before I forget. So we have this transparency value in here. Obviously, for air blocks, I don't think we actually reference air blocks. I think we just count one as transparent, but just in case. Render neighbors wants to be true, and transparency is 1. That means 100%. All of these, we don't want to render neighbor, and we don't want to have any transparency, so we can just leave those. And then we get down to glass. Transparent, we want to render neighbors, and transparency wants to be 100% or 1. And leaves are a bit different. We want to render neighbors, but transparency wants to be, let's say, 0.8. So it blocks some light, but not all. Actually, I'm going to set it to 0.5 so that we can see the difference. It would actually be something like 0. If you were going like proper Minecraft, it would be something like 0.8 or 0.9, because leaves block a little bit of light, but not a lot. And then obviously we're going to struggle to see that. We want to see some results here. So I'm going to set it to half transparency, so we'll be able to see a shadow, and it will clearly be a different amount to the other blocks. And I've just noticed we've got an error here. Let's just see what that is. Undeclared identifier. Oh, yeah, that should be global light level. I'm sorry if you noticed that when I typed it and have been screaming at the video since. And also, there should be a semicolon there. There we go. Right, now if we go back into chunk. So that sets our light ray to whatever that current transparency is. If we're passing through air blocks, then the transparency level is unaffected. It would still say 1f. However, if we hit a leaves block, it would be modified. It would be set to 0.5. And then the light ray would be 0.5 going onwards, because any block that is underneath that leaf block is going to be 0.5. And then simply we set this voxel dot global light percent equals light ray. And then we just hand that all back to our voxel map. And then the only thing left to do is to actually call that, which we will do here, just after clear mesh. And I've already forgotten the name of it. Calculate light. So now if we run this code, you can see we have some not quite 100% dark shadows. And if I stick a solid block here, we should have a darker shadow. There we go. It's not quite the difference that I was hoping for, but you can see that one's darker. I'm just going to make these values a bit more obvious, just so that we can see it in action. So leaves, we will make it closer to where it actually is in the game. We'll go 0.75. Let's try that again. There, so those shadows are a lot lighter now. And then if we stick a solid block there, we should be able to see a much darker shadow. And then if we go in our inventory, just for the sake of it, if you remember, this last one is actually a leaves block. It's just because I haven't put a leaves icon in there. But don't worry, the video after the next one, when we've done the Unity jobs modification, we're going to go over making a proper system for importing the block data. We're actually going to import it from an external file. So there's that to look forward to as well. So if we stick a glass block there and then a leaves block there, we should have 3 different levels of shadow. As you can see, we have one dark, and let's just stick a grass block there so you can see properly. One dark, obviously glass puts out no shadow, and then one light for the leaves block. So that's working. However, we do have a problem here in that if I put a solid block there, we get a shadow, which is correct. We want a shadow there. However, if I put a leaves block back there and I put a solid block above it, we don't get a darker shadow. And that's because the light ray is working its way down and it's setting itself as the value of whatever the block it's going through currently is. And the last block it went through before it got down here was this leaves block. So even though there's a darker block above it, a more opaque block above it, it's using this leaves block as its value. If I delete that, we get our dark shadow back. So we need to fix that now. And that is nice and easily fixed by, if we go into our light function, and in this if statement here, we're just going to simply add and world.blocktypes this voxel.id.transparency is less than light ray. So it's only going to modify the light ray if the voxel is more opaque than the previous one. So now, as you can see, we have a semi-transparent shadow there, like half of, or 0.75 of the available light range. And if I stick a block there, we get a dark shadow, even though there's a leaf block underneath it. So that's that part fixed, but that's not really why we're here, is it? We need light fall off. So back into our calculate light, and let's we're in the home stretch now. Before the for loop, we're going to create a queue, and the queue is going to be a bunch of vector3 ints, and we're going to call it lit voxels. That's going to equal a new queue vector3 int. And then we're going to go down to the bottom here after we've finished all this maths here. We're going to say if light ray is less than voxel data dot light fall off. Sorry, not less than, greater than. That will make no sense whatsoever. If it's greater than light fall off, lit voxels dot on queue new vector3 int x, y, z. So basically the light fall off is our increment value or de-increment value. In Minecraft, the light levels are something like 1, 2, 3, 4, 5, you know, whole numbers, 0 to 16 or 15, I can't remember exactly. And when you have a light source, and bearing in mind that a light source could be a torch, it could be a glowstone block, but it also could be a block that is directly under sunlight, which is what we're dealing with here. It's any block that is not completely dark. The light fall off is the amount that the next block, which is not lit, next to it will be darker. So you have one block which is going to be 100% light, and then let's say our light fall off value was 0.1. The next block would be 90%, 0.9. The next block would be 0.8, and so on. So that's what the light fall off value does. So any block that's less than the light fall off value, we're not interested in because it's too dark to illuminate anything else. We're only interested in blocks that are bright enough to actually affect neighboring blocks. So then we go down to the outside of all of our for loops, and we're going to create a while loop. And we'll say while lit voxels dot count is greater than 0. And the reason we're using a while loop is because we're going to be adding voxels to this queue while we're operating this loop. So that number is not just going to go straight down. Like, voxels will be added to it as we're working on them. But don't worry, we're not in danger. You'll see why, but we're not in danger of creating an accidental infinite loop here. So for each, actually, let's just copy this line of code up. So then we want to do a loop of all of our faces. So int p equals 0, p is less than 6, p plus plus. So same as when we check our neighbors, that's all we're doing here. Like, light doesn't travel diagonally in Minecraft, or at least not directly. It travels diagonally in the sense that it will go forward and then right, which is technically diagonally, but it doesn't go diagonally. So we don't need to worry about the diagonal neighbors. It's only the front, back, left, right, up, down neighbors that we're concerned with. So inside this loop, we're going to create a new vector3 current voxel equals, oh, sorry, actually, we need to get from our queue first. So we're going to say vector3, and we'll call it v equals litvoxels.dq. So that, if you remember how queues work, that will automatically remove the topmost item in this queue. Everything else gets shuffled up one, and this item, by the act of dequeuing it, means it's no longer in that queue. And then current voxel is going to equal v plus voxel data dot face checks. And the way vector3 ints work, you can add a vector3 int to a regular vector3, which is what we've just done here. However, we do want it as a vector3 int. So vector3 int neighbor equals new vector3 int, and then we just want to recast all of our current voxel values. Too many brackets. So now we've successfully gotten our lit voxel out of the queue, and we have gotten a neighbor voxel value as well. So now to do some work on those neighbors. So the first thing to do is say if is voxel in chunk, and pass in neighbor.x, neighbor.y, neighbor.z. Now, we're going to end up with some weird artifacts here because we're not going to handle cross-chunk lighting in this video. That's going to be in a different video because we're going to slightly mess around with the way chunks work in the next video when we implement Unity jobs. So it's kind of a minor thing. You'll see it if you have lighting shadows crossing over chunks, but for now we're only going to deal with in-chunk lighting. So this ensures that we're only dealing with stuff if it is actually in a chunk, and there needs to be a second bracket there. If it's outside of the chunk we're working on, we'll just leave it alone for now. I'm just going to copy this because we're going to be using that string of text again. I'll say if voxel map and the neighbor values dot global light percent is less than voxel map, and then we want our current voxel. So remember, neighbor is obviously the current neighbor that we're looking at. V is the voxel that we started with, the one that is lit. So v.x, v.y, v.z dot global light percent, and then this needs to be minus voxel data dot light fall off. And the reason we need to do that, I'll just stick the brackets on there. I believe I must have missed some brackets somewhere. All right, sorry, I haven't missed some brackets. I've added an extra bracket. So the reason we have to add that light fall off is because it's not just important that the neighbor's light percentage is less than the current voxel's light percentage. It needs to be less than by at least a light fall off amount. Otherwise, it's not dark enough for this voxel to illuminate it. So if it is that much darker, at least, then we can modify it. And then the modification is basically just voxel map neighbor dot global light percent equals, and then we'll just copy this whole string here, equals our voxel minus light fall off. And then what we want to do after that is check if the current voxel that we've just edited, i.e. our neighbor voxel, so we'll just copy all that, if that value is greater than voxel data dot light fall off, then that means that this voxel that we've just made a little bit lighter because it was next to a lit up voxel and it's darker, it means that this voxel, even though we've made it darker, is still light enough that it could potentially illuminate some neighbor blocks. So in that case, we want to add it to our voxels, lit voxels queue. And I think that should be all of it. So let's just try that out. So it's not the easiest to see with the trees, but you can see a definite fade off there between the darker bits and the edge of the shadows and all that. So what I'm going to do now is I'm going to mess around with the values a little bit. Oh, sorry, I'll just show you the chunk thing that I was talking about. It's kind of a sharp edge here where the shadow's not quite blended as properly. So that's where a chunk edge is. So we'll fix that in when we've added our Unity job system, but for now we'll just have to live with it. So what I'm going to do now is I'm just quickly, that's the end of the video, we've done all the coding. I'm just going to mess around with the light settings to make the shadows more pronounced and make everything stand out a little bit more, and I'm just going to show you the light, and then dig a hole basically and show you the light effect more pronounced so you can see it in action. And just before I forget, actually, we need to change, because we've reversed the way we take in our light value, we need to change this so that the bottom value is 0 and the top value is 1, and you no longer need to clamp the value to not go completely to 0, which will be 100% black, because that is handled here, so it's never going to go below 0.1. And the other thing that we're going to need to change, because we've reversed that value, is we want these two flipped round. Otherwise we're going to have a perfectly bright world with a night sky. So I'm going to go dig a hole, and I will see you in a second. So there, I just thought I'd dig a nice hole in the ground so you could see the lighting a bit more obvious. Like I say, you can play with the values, you can make things darker, you can make things lighter. There is the weird effect between chunks at the minute, but like I say, we're going to fix that in not the next video, but the video afterwards. And that is it for now. I'm sorry it's not a perfect lighting system right now, it's just that some of the stuff we need to do in the next video will interfere with the lighting system. So I don't want to put a load of stuff in this video that we're going to have to undo. And there was always going to be another part to the lighting system anyway, so hopefully you can bear with me. But that's it for this video, and I will see you next time. Bye bye.